Yeah, sure. First of all, welcome everybody. So finally, we are here on 23rd Annual International Mars Society Convention. So today I am here to talk about my research on advanced power generation system for colonization of Mars using atmospheric carbon dioxide. So when you read the title, you can see there are a few keywords like power generation, colonization, and Mars. So let us start up talking about them. So this research work is done by Mr. Ramesh Kumar, my mentor, and me. You can see us on the slide. So moving on. So all of us have heard that we are going to colonize Mars. We are going to get humans on Mars. So what's special about Mars? Why Mars and not any other planet? So Mars is having most properties like Earth only. Its soil has some water content in it. It's in a favorable habitatable zone in our solar system. That means it's not too far away from sun and neither too close. So it's not that hot and not that cold. But you can expect some chilly winter. As you can see, Mars orbits sun in a very different orbit as compared to Earth. So there is enough sunlight that we can use solar panels. The next major thing is the gravity at Mars is 38% of that of Earth, and that is because you can see the mass of Mars is very less as compared to Earth. But this is adaptable for human body. We can survive with this gravity. Also, Mars have an atmosphere, although it's very thin, but still something is better than nothing. And day-night rhythm is quite similar to that of Earth. It's few minutes more than 24 hours. So if we need to colonize Mars, or if we need to colonize any planet, what are our basic needs? First of all, we need human for that. And after, what are the needs of human to survive? So you have just ask yourself, what do you want to survive on a daily basis? You need basic utilities, oxygen, power, food, and as it is interplanetary colonization, so you must need an interplanetary transport system. So you need propellant to power your launch vehicles and all. Now the problem is that all this requires power. So we can say the essential step for colonization of Mars is essential power generation for Mars. How are we going to solve the power generation problem? So here is what we have proposed. We have proposed a supercritical Brayton cycle that will operate on atmospheric carbon dioxide as operating liquid. So you can see here it is a Rankine cycle, and here is a supercritical Brayton cycle producing the same amount of power. So why is it so much difference in their size? So here are the reasons. Like when a turbo machinery is working on a supercritical fluid, the density of supercritical fluid is much larger, like a liquid. But there are some properties like gas also. Supercritical state is somewhere between liquid and gaseous phase. And that is why the size of turbo machinery get reduced very compact, and the efficiency that we can obtain with that compact size is unmatchable. You can see that Rankine cycle efficiency is 33%, but supercritical CO2 goes to about 40%. Now, why supercritical Brayton cycle on Mars? So let us see Martian atmosphere. Let us read it. So you can see that Martian atmosphere is 100 times thinner than Earth. And this is the point that is most favorable for us. It has about 95% of carbon dioxide. And as I mentioned earlier, we are using carbon dioxide as our operating liquid. So this comes in our favor. But there is also some problems here. You can see that atmosphere is 100 times thinner. That means very less atmospheric pressure. So atmospheric pressure on Earth is 1 bar and atmospheric pressure on Mars is 0.006 bar. That's very less as compared to atmospheric pressure on Earth.
I'm absolutely
What does that mean?
flabbergasted.
That means that we have to do
Shit.
more compressor work to compress our gases to that specific critical pressure. So let's see what's our objective. It's clear that we are going to make Mars habitable, so we are going to develop a power generation technique for Mars. So far, I have discussed supercritical Brayton cycle and how we are going to optimize it. We are going to use Martian atmosphere for our favor. Martian atmosphere consists 95% of carbon dioxide as discussed earlier. Now the main catch here is due to second law of thermodynamics, we have to provide some heat and there should be a heat gap between source and sink, and that heat gap decides that how efficient your system is. So in our study, we took that heat source as a nuclear fission reactor. So in simple words, we can say that we are planning to design a power plant in accordance with Martian atmosphere. So here is the concept that we are following. The basic idea here you can see actually the temperature versus specific entropy gas of supercritical carbon dioxide, and this is the supercritical carbon dioxide vapor dome. So you can see that supercritical carbon dioxide reaches its critical pressure at 7.7 megapascals and very low temperature of 30 degrees Celsius. That is very low as compared to other like water and other gas what we have and liquid what we have. So it is very easy to make carbon dioxide reach its critical state. So we intend to compress the atmospheric carbon dioxide from 0.006 bars to 7.7 megapascal, and then we intend to add heat in it using our nuclear fission reactor, and after that finally we are going to expand it on turbine, and there will be a shaft that will be connecting whole system and that will be connected to a generator. So heat energy of nuclear reactor will be connected to mechanical energy of rotating turbines, and finally that rotating energy will be converted to electrical energy through a generator. So here are the challenges. This whole system needs to be installed on Mars. We need a nuclear reactor small and safe enough that it can be carried from Earth to Mars. And this is the crucial challenge here. We need to compress carbon dioxide from 0.006 bars to 7.7 megapascals. Now, that requires a very huge pressure ratio on both sides of compressor end. So here are the assumptions that we have made. Certainly, we are limited by technology of our time, but I do believe that we will overcome it someday. So we assume that we have enough capability to transport this large components and whole system to Mars. We are capable to build a miniature nuclear reactor, and we have somehow manufactured a compressor having high compression ratio capable enough to pressurize carbon dioxide to its critical pressure. Now, let's understand what supercritical. So you can see here, this is temperature versus pressure graph, and above this line lies solid phase. It is triple point where all three states coexist together. And this line here is gas. Below this line there is gaseous phase, and between here there is a liquid phase. Now, what is this critical point? Critical point actually lies in the intersection of critical pressure and critical temperature. Critical temperature is defined as the temperature after which a gas can't be liquefied no matter what amount of pressure you apply. And the pressure corresponding to critical temperature is known as the critical pressure. So you can see above this critical point there is supercritical fluid. So what is this supercritical fluid and how carbon dioxide behaves when it is in its supercritical form? So here are the basic properties like what is required to make carbon dioxide reach in supercritical form. Here you can see that actually it requires very less temperature and very less pressure as compared to other gases and liquids that what we have. So when carbon dioxide is in supercritical condition, it will have following properties. It will have low viscosity like a gas, high diffusivity like a gas, no surface tension like a gas, high solid power like a gas, high compressibility like a liquid, and high density like a liquid. So you can see that in supercritical stage, carbon dioxide exists both in liquid phase as well as vapor phase, and it's very dense at its supercritical stage. So that compact size of turbo machinery that we are going to need to design our whole system. So let's talk about Brayton cycle because it is what we are going to use. So this is simple Brayton cycle. Here this is ideal one. Ideal one because you can see it's isentropic compression. If it would be a real one, the process would be adiabatic. So you see we have a compressor that compresses the working fluid, whatever it is. Let's say that it is an air Brayton cycle, so our working fluid is here. So here the compressor compresses air, then it is sent to combustion chamber where heat is added and then after it gets and see here is a catch that the work obtained here is also used to drive this compressor. So efficiency of Brayton cycle is limited to back work ratio. How much amount of work is doing the shaft is doing to run the compressor. That is what limits the efficiency of normal Brayton cycle. Here you can see the trend of efficiency with respect to pressure ratio. Now we are saying pressure ratio a lot. So what is pressure ratio? Pressure ratio is nothing but the ratio of pressure over here at the end of compressor and over here at the beginning of compressor. So you mark it as 1, you mark it as 2, so pressure ratio is nothing but P2 by P1. So you see if you increase the pressure ratio, the efficiency keep on increasing and after a point it will be constant. Now let's see what is intercooling. So see
Repeat that part. We
when the
can't
gases
hear
are being
you.
increases the
Hi, sorry to interrupt you. This is Carrie. You're starting to break up in and out. Is your microphone going on and off, or?
I think it's a network issue.
Oh, okay.
Am I audible right now? Am I audible right now?
I can hear you now. Yes, go ahead.
Okay. So let's see what is intercooling. So when we use multi-stage compressor, like more than one compressor, what happens that this compressor is also increasing the density along with the temperature. Now the temperature is going to increase, so the amount of heat added in the combustion chamber will be decreased. That means we are wasting a lot of heat. So in order to tackle that problem, we use an intercooler. An intercooler is just a heat exchanger which reduces the temperature of exhaust of one compressor before entering it into another compressor. So what happens here, if we apply intercooler here, let's say that air is rushing in from compressor 1 and it is a certain temperature. After passing through intercooler, the temperature will be less when no intercooler is applied as compared to when there is no intercooler is applied. So we have more heat capacity, we have more heat, what can you say, absorbing ability of that fluid in combustion chamber. So very less amount of heat is wasted. So it increases the efficiency and it also increases the volumetric efficiency. Now, what is volumetric efficiency? It's nothing but heat absorbed by a particular amount of volume that is being pumped in through compressor. So let's see now what we have planned for a nuclear reactor combined cycle with Brayton cycle. So we are planning to integrate recompression and recooling. So we have already seen what recooling is. Let's see what recompression is. So what happens in recompression? The turbine expands the gases not to nominal or ambient pressure. It expands them a little higher than the ambient or pressure, and then those outlet gases which are having pressure a little higher than the ambient pressure are fed into another compressor. Now what does this do? This reduces the amount of work done by the compressor. As I mentioned earlier, the efficiency of Brayton cycle is limited by the work fed to the compressor. So what is this doing? This is reducing the work done by the compressor. So what we will have as a result, we will have increased efficiency, but we have to add another compressor and we have to add another heat exchanger. So it is adding extra weight to our whole cycle. So after all these studies, now that we have known that what we are doing and why we are doing,